The very first gravitational waves appeared in the instance after the Big Bang. These first ripples in space-time, which were caused by quantum fluctuations in the fresh primordial soup of matter, were swiftly magnified by inflationary processes, which caused the cosmos to rapidly expand. There are gravitational waves in the universe that were created roughly 13.8 billion years ago. Welcome back to my channel. Finding the first gravitational waves in the universe. However, the crackle of gravitational waves created by more recent occurrences, like as the collision of black holes and neutron stars, drowns them out. Gravitational waves are being detected on an almost daily basis by LIGO and other gravitational wave detectors, but primordial gravitational signals are several orders of magnitude fainter than what these detectors can register. It's expected that the next generation of detectors will be sensitive enough to pick up these earliest ripples. The new technique might be used to uncover hidden traces of the first gravitational waves in the universe. Over the course of the following next 10 years, more sensitive detectors become available. The structure and characteristics of these primordial waves may then provide information about the early cosmos, including the circumstances that led to inflation. Using the technique we have developed, these primordial gravitational waves can then tell us about processes in the early universe that would be otherwise impossible to study, if the strength of the primordial signal is within the range of what next-generation detectors can detect, which it might be. The cosmic microwave background, or CMB, which is assumed to represent radiation that is left over from the Big Bang, has received the majority of attention in the search for primordial gravitational waves. The electromagnetic spectrum's microwave band is where this radiation is most evident today, permeating the entire cosmos as energy. The B modes, a type of delicate polarization pattern, are thought to be the remnants of the primordial gravitational waves, which rippled out and left their mark on the CMB. Others are searching for the ripples directly in the gravitational wave data, as others continue to search for primordial gravity waves in the CMB. Any gravitational wave signal that results from an astrophysical source, such as colliding black holes, neutron stars, or exploding supernovae, has been referred to as the astrophysical foreground and has generally been attempted to be subtracted away. Physics experts can only estimate the softer, non-astrophysical signals that might contain primordial waves after removing this astrophysical foreground. The issue with these techniques is that the astrophysical foreground contains weaker signals, such as those from farther off mergers, which are difficult to predict in the final subtraction and are too faint to be seen. In order to describe the more evident conversations of the astrophysical foreground in their novel method, the researchers used a model. The model forecasts the gravitational wave signal pattern that would result from the collision of astronomical objects with various masses and spins. In order to mimic gravitational wave patterns from merging black holes and other strong and weak astrophysical sources, the researchers adopted this model. In order to, for example, determine the masses and spins of binary black holes, the physicists attempted to characterize every astrophysical signal concealed in this simulated data. As they now stand, these characteristics are only weakly limited for the weakest signals, and easier to recognize for louder sounds. The new method accounts for the uncertainty in each pattern characterization, and is therefore able to detect the presence of the weakest signals, even if they are not well characterized, in contrast to previous methods that only use a best guess for the parameters of each signal, in order to subtract it out of the data. They were left with more random primordial gravitational wave signals and instrumental noise, particular to each detector, after they had discovered such distinct, non-random patterns in the gravitational wave data. The researchers proposed that since primordial gravitational waves are thought to be a diffuse, persistent hum that permeates the cosmos, they should appear the same in any two detectors and so be coupled. The remaining random noise that a detector receives, on the other hand, ought to be unique to that detector and unrelated to that of other detectors. For instance, depending on the location of a given detector, the noise from surrounding vehicles should differ. The parameters of the primordial background were extracted by comparing the data in two detectors, after accounting for the model-dependent astrophysical sources. By initially recreating 400 seconds of gravitational wave data, and scattering wave patterns that represented astrophysical sources like merging black holes, the researchers tested the new technique. Additionally, they introduced a signal into the data that resembled the enduring hum of an ancient gravitational wave. To test if they could reliably detect any black hole mergers as well as the pattern of the wave they injected, they divided this data into 4-second parts and applied their algorithm to each segment. They were able to successfully retrieve the hidden, primordial backdrop after carefully examining each data segment throughout numerous simulation runs and under various initial conditions. In order to separate out the primordial signal, the new method will be able to cross-correlate and evaluate data from 2 different detectors. When that happens, researchers could have a helpful thread they can follow back to the circumstances of the early cosmos. It is obvious that the research is on. I will keep you updated as soon as new progresses are made on this matter. Thanks for watching.